Hello everyone and welcome to the World's Marina channel. We today talking about DLD, an important subject in engineering. DLD stands for digital. Sorry, my pen is a little. Digital logic design. Sorry about that. I'll just switch the marker. So DLD stands for digital logic design. So this. Why we are using this? What's the importance of it? Digital logic design is used is the importance is because we use it in constructing hardwares. So you know the hardwares in the small chips in your phone, the small chips in your CPU, the small chips in anything, your smartwatches. It all uses digital logic design. Even in the video games, PS4. So what we do is we use coding, or we use the knowledge to construct the hardware. That's what we do in this one. So digital. What is digital? For those who don't know, sorry, I'll let you know now. This is an graph. This is an x-axis, this is y-axis, this is an analog signal. Analog, so you might be familiar with this because it is showing a sine wave. So this is an analog signal, so this whereas is a digital signal. So what's the difference in this between these two? In the analog signal you have values that are continuous. There's no discrete value, while in digital the values of the signal are discrete. So you can see either it's some value at a point from, let's say, I'll make it here. So from this time, from starting from 0 to starting from to t, the value of the signal is 1. 0 to t, value is 1. Let's say this time is t plus 1 and this is minus 1. So for t plus 1, from t, from this to this, t plus 1, the value is minus 1. So there is a value, a discrete value at a time. You will know more further when I continue. Okay, the main thing in digital logic design, you don't have to remember many things. It's very simple. Value, that's a 0 and a 1. 0 here, for now you can think as it's off, while 1 you can think of it as on. Just imagine this is a light bulb. I'm sorry, my drawing is not that good. So it's a bulb. So when it's 0 it will be off, while if the bulb is on, the value is 1. So from now I'm not gonna say on or off, I'll say 0 or 1, right? So you got the idea of 0 and 1, right? Okay, so let's jump into some basic things of digital logic design. There are things called gates. Yeah, you are right. Same like you have a home and you want to enter this home. And how to enter this home? You need, to enter this home you need a gate, right? Same like in digital logic design, there are gates. And those gates, when, let's say this is a gate and someone goes inside it and something is happening in that gate and there's an output. So firstly there will be input and there's output, right? Okay, I'll not make more confusing. Let's jump into the basic thing, then you will get more knowledge of this thing. So we have gates. Gates is same like a door, right? So let's say the first gate is OR gate. I'm giving a name called OR gate, right? These are basic gates. These are basic building blocks. From these gates you can build up a very complex system, such as rocket launching system, something like that, election system. So you can make all these things from these basic gates. That's why we need it. So for OR gate, the representation of the OR gate is something like this. Sorry, a little curvy. You can see this is the representation of OR gate. If you want a more detailed photo of this, you can Google it. So these two things, you can see these two wires going inside. These are kind of a wire, you can say, and there's a wire coming out of it also. Let's say this wire I name it A, and this wire I name it B. Well, this wire coming out I name it out. So there are two wires going inside and one wire going out. So what happens, this is the representation of OR gate. There are two inputs. These are inputs. These are output. This is one output only. Then we make a thing called truth table. Truth table. Why the name is truth table? Why? Because it's always true. No matter what happens, this table will always be true for OR gate. Doesn't matter what conditions, this thing gonna be true. It's a universal truth. Okay, we know truth table is some table which is a table which is always true. But what this table tells us? It tells us that what will be the output of the OR gate if we are giving some inputs. Let's say the first input I give in A, the wire A is 0. That means off. For now you can say it's 0. And B is also off. So the output for the OR gate will be 0 as well. If it's hard to understand, you can just remember these values. So A is off, B is off, then output will be 0. Let's say A is 0, I turn it off, and B is on, then the output in OR gate will be 1. If I put A as 1 and B as 0, the output will be 1 still. If both are on, the output will be still 1. What the heck just happened? You might be thinking right now. So what is happening here right now? Let's say if A and B both are 0, the output will be 0. If A and B are both off, then the output will be off. If either one of them is on, you can see in these three cases, either one of them is on, it will be on in OR gate. So here you can see A is off, B is on, output is on. Whereas A is on here and B is off, it will be on still. In the last case, you can see both are on and it still will be on. So this is a truth table. You have to remember these values, right? Even if, let's say, for just an understanding, if we have three inputs, let's say A, B, C, put it here. If either one of them is 1, then the output, if you are saying 1, that's correct. Because in OR gate, either one of them should be 1, the output will be 1. If all of them are 0, the output will be 0 as well. Let's move on to another gate. That was OR gate, and now we'll be talking about another gate which is known as AND gate. And if you still don't understand, I can tell you like this. If A, you can think about it like this from the name itself, or if A is on or B is on, if one of them is on, it should be on. Let's move to another gate, AND gate. The representation of the AND gate is something like this. For better graphical image, you can look at Google. let's say if our AND gate is again having A and B is out input, and there's one wire going, that's output. And surely you have to draw like this. You cannot draw like this, that it's having two outputs. That's completely wrong. Don't do that silly mistake. So this is the correct diagram. Simple AND gate. Let's create another truth table, the table that tells truth. We have A, we have B, and we have output. Let's say if A is 0, B is 0, in AND gate output will be 0. If A is 0, B is 1, the output will still be 0. If A is 1, output B is 0, output will still be 0. If A is 1, B is 1, output will be 1. If you're confused, you can think it like this. In AND gate, all the inputs should be on, or all the inputs should have value 1, then only it will be 1. Otherwise, the value of output, if none of them is, any of them is 0, output will be 0 as well. That's the truth table. And you might be thinking, why only have these 4 values? That's only the why this, are there any more values? Are there any more values we can add in our input? No, we cannot. To test that, there's a formula called 2 to the power n. How many, you can say, rows here, how many rows we can make? You can get it from here. N here is the number of inputs. Here in this case we have 2 inputs, so 2 to the power 2, which is 4. So you're gonna have 4 rows. You can see here 1, 2, 3, 4. But when we are writing rows in DLD, in science, we are science students, we are engineers, we're gonna start with 0. 1, 2, 3, but ultimately it's 4. 1, 2, 3, 4. That's the truth table for AND gate. Moving on. Another gate is called NOT gate. NOT gate. Yes. The representation of the NOT gate is like this. I'm so sorry, my drawing is not that good, but please Google the image. Here you can see what is happening is there's only one input and one output, and this thing, this is known as bubble. You don't have to write it, but just for your knowledge, bubble. So here's one input with one output. What is this NOT gate? What the heck is it? Let's apply that formula as well, 2 to the power n. How many rows will be there? Will it be 4 in this case or not? Let's see. So we have only one input, so 2 to the power 1 is equal to 2. That means we're gonna have only 2 rows. So rows, we start with 0, 1. That's it. 2 rows. We have 2 rows. That's correct. This formula is correct. So what happened in the first case? If I have a value, if I put A as off, this NOT gate is a stubborn gate. It's like a stubborn girlfriend. You do something, she'll never be happy. And if the value is A, you have done something, she will still be like saying something else. The output will be 1. You wanna go coffee? She'll say, no, I wanna drink juice. And you say her, that your girlfriend, that I wanna drink a juice, baby. But then she'll be like, no, I want a coffee. So this is the NOT gate. It will just invert. Also, this gate is known as inverter. Some people call it inverter. Yes, INV, inverter. Not the inverter at your home, but that's doing something similar. So this is NOT gate. That's a truth table for NOT gate. Moving on. Then we have a thing called NAND gate. NAND. So with the NAND gate, NAND. So what happened in the NAND gate? There is an AND gate, and there is a this bubble means, I told you this is a bubble. Bubble means inverter, means this is changing the values. It's inverting. It's a NOT gate here. You can say here NOT gate is here. Okay, let's create a truth table for it. A, B, and output. Let's create a truth table for it. A, we have B, and we have output here. This column, I'll call it C. I'll tell you why. So what happened here, you know, 2 to the power n, so there will be 4 rows. You can always write down if you want. 0, 1, 2, 3. It's very helpful if you write down. So 0, 0, 0, 1, 1, 0, 1, 1. These are the values here for our NAND gate. So what happened in the AND gate first? Because here first, you can see here is an AND gate first. Here I call it C. Before an inverter, before this output, there is a NAND gate. So let's see what happens. A, B, 0, 0 in AND gate. You know, like either one should be 1, both should be 1, then it will be only 1. So for this is 0, this is 0, this is 0. I want you to have a look at AND gate if you have confusion again. So C is before the inverter, that's why it's having values like this. And after this, what happened? We have an inverter. The C goes to the bubble. That means the C is getting inverted, you can think like that. So what will be the output? You know, if it's 0, it will become 1. If it's 0, it will become 1. Girlfriend, you saying you want to drink juice, girlfriend say no, I want a coffee. You want to drink a juice, girlfriend says I want to drink a coffee. So this is the NAND gate. Moving on, we have another gate called NOR gate. NOR gate. You're correct. If you have guessed right, that's true. It's a mixture of OR gate and an inverter. Same, we have 2 inputs, 1 output. A, B. This, let's call this output. This thing is C here, and that's output. 2 to the power n. You're gonna have again 4 rows. 0, 1, 2, 3, 0, 0, 0, 1, 1, 1, sorry, 1, 0, 1, 1. You will practice, when you practice, you will even remember these values. So what happened in the OR gate? If they both are 0, they are 0. If either of them is input is 1, it will be 1. So in this case, you can have a look again at the OR gate if you want, because either of them, here is CB is 1, so C is 1. A is 1, C is 1. Doesn't matter if B is 0. Here both of them are 1, surely it's going to be 1. Now let's invert them. Your girlfriend comes here again. You want to drink a juice? No, she wants a coffee. You want to drink a juice badly. She wants coffee. You want coffee. You want coffee. You stupid idiot. You want a coffee. That's the truth table for NOR gate. Let's move on to one of the, again, one of the important gate again, which is known as XOR gate. XOR gate, or we will call it exclusive OR. So the representation is like something like this. Just draw it like this. For better purpose, just have a look at Google. C is our output, two inputs, 0 0 0 1 1 0 1 1. What happened is here is that if both you have two girlfriends, B, if both of them aren't with you, your girlfriend A is not with you, your girlfriend B is not with you, then output you are sad. If B is with you but A is not with you, you are happy, man. And if girlfriend A is with you but B isn't with you, you're still happy, because we don't want them to be together. Oh, one day you met both of them together, your life is ruined, your life became hell, you are unhappy. So this is XOR. For now, this is it for the basics of DLD. In next video, we're gonna talk more details about truth tables, more complex designs of digital logic design. See ya!